taking the derivative. Okay, perfect. It's recording. Okay, so 5.4 is the first derivative test. Okay, the first derivative test is when we use the first derivative to test whether or not a function has a maximum or a minimum. So first derivative test, test whether or not we have a maximum or minimum. Okay, so it says start with something we know. A quadratic function's graph is a parabola. And we know that the function f of x equal to x squared minus 4x minus 2 opens up, so f will have a minimum. So it's talking about the graph to the right. We know that the graph of a quadratic is a parabola. Since a is positive, we know it's going to be opening up, which gives us a minimum value at what x value? 2. Okay, right here. So it says, examine the graph of the parabola and describe the behavior of the derivative around the minimum. So what it's talking about is from this part of the graph all the way to the minimum, how would you describe the derivative? Just the part I highlighted. Decreasing, yes, decreasing. So we're pulling from the notes from yesterday. And say that again? Yeah. Okay, yes, you could say decreasing at an increasing rate, but how would we write that with our symbols, just like we did yesterday? Or the day before, sorry. F prime of x is less than 0. Okay. What would the other side be? Greater than 0. So f prime of x is greater than 0. Okay. Which means at our minimum value, what is f prime of x?
0.
Equals to 0. Okay, so we're describing the slopes around this function, and we can notice that when we get our minimum value, the sign of the derivative is changing. It goes from a negative less than 0 to a positive greater than 0. So that gives us the following rules. It says the derivative of the function, if it's going from negative to 0 to positive, we have a minimum. Okay, just like we see in our diagram. What would represent a maximum? Positive 0 to negative. That would be a maximum. Okay. So I put 0 there as the placeholder because in our example, the derivative of f equals 0 for our maximum and minimum. What would be another way that the derivative could be a critical point? Cusp. And what does a cusp tell us? That the derivative does not exist. So you could replace 0 with does not exist or an undefined value on the function. Okay. So when you're asked to justify your answer, so let's say they say find the minimum or maximum value and then give a justification. You're going to mention just that. You're going to mention how the sign of the derivative changes, and you're going to talk about how it changes. So in this example, it says assume C and D are critical numbers of the function f. There is a minimum value at x equals c because f prime of x changes sign from negative to positive, just like we talked about above. And then it says there's a maximum value at x equals c because the derivative changes signs from what? Positive to negative. Okay, so for the examples, I would try to write smaller than you typically write. We have a lot to write. Okay, Number 1 says use the first derivative test to find the x values of any relative extrema of f of x is equal to x squared minus 4 to the 2/3 power. So remember, when it's talking about relative extrema, it's talking about when we have a potential critical point. And we just said that that could happen if the derivative is equal to 0 or if the derivative does not exist. Okay. So in order to use the first derivative test, we're going to take the first derivative. So f prime of x is equal to, we're going to use the power rule and the chain rule. So we have 2/3 x squared minus 4 to the power of negative 1/3 times 2x. Okay, I brought down the exponent of 2/3, subtracted 1 from the exponent, and then took the derivative of the inside function. Okay. I'm then going to make it pretty. Right? I'm going to get rid of that negative exponent, put it back in the denominator, and then simplify anywhere I can. So when I do that, I get 4x over 3 cube root of x squared minus 4. Okay, so I got the cube root on the bottom because this is x squared minus 4 to the negative 1/3 power. Okay. And then I got 2x times 2/3, which is 4x thirds. Okay, that's where everything came from. So my goal is to see when I can make this derivative equal 0 or when can I make it not exist. So the first one, I know that I can make it 0 if I set 4x equal to 0. Because 0 divided by anything gives us 0. Okay. What would I have to set equal to 0 in order to find the ones where it makes the derivative not exist?
Make
the bottom equal to 0. Okay. Or I can just set what's inside that radical equal to 0. Because if I start to get rid of all that, like divide by 3, cube both sides, it's not going to affect the equation any. So I'm just going to set this part equal to 0. Which means I have x is equal to 0 and x is equal plus or minus, both of them, right? Plus or minus 2. Because if I add 4 over, I have x squared equals 4. And if I take the square root of something that's squared, I have 2 possible answers, plus and minus 2. Okay, so from here, I'm now going to set up my table like I did before. But to save some space, instead of writing my intervals and then picking a number and writing that number on the table, I'm just going to write my intervals on the table. Okay, so I have x and then f prime of x. So since my potential critical points are 0, negative 2, and 2, what would be my first interval? Like my interval of values. Negative infinity to negative 2. Negative infinity to negative 2, which means I am at my critical point, negative 2, and it was a critical point because it was 0 or undefined? Undefined. Right, because that negative 2 came from setting the denominator equal to 0, so it came from undefined. What's my next interval? Negative 2 to 0, which leaves me at my critical point 0, and I got that 0 because the derivative was 0 or does not exist? 0. Okay, so I write 0. What's my next interval? 0 to 2. Which leaves me at my critical point 2, and I got that when the function was undefined. And then what's my last interval? 2 to infinity. Okay, so this is where, like I said, if your algebra skills are not that great, you can utilize Desmos. So for each of these intervals, yes?
Oh, can you explain why that -2 is undefined again?
Yes, the 2 and the -2 are undefined because we set the denominator equal to 0. And if the denominator equals 0, then we end up with something that's undefined. So it'd be like 4x over 0. Okay. So what I would do on Desmos is I would type this derivative on the first line. And then on the next line, I would put x equals, and then you pick a number. Okay? And it should give you an intersection on the graph. If you hover over that intersection, it will let you know if that's a positive or negative value, because that's all we care about. Okay? Or you can pick a number in the interval. So for example, in that first interval, what could we pick? -3, right? And then you could go to this, okay, do some mental math. We would say 4 times -3, and then 3 cube roots of 9 minus 4. We know that the bottom is going to be positive, and the top is going to be negative, so our sign we're going to write is negative. Either way, you either do a mental check with the derivative or you use Desmos. Okay, so you would do that for every single one. So on the next one, you could pick, let's say, -1 and try. When you do that, you get positive. On the next one, you could check 1. You would get negative. And then on the last one, you could check 3, and you would get positive. So no matter which way you're choosing to do this, I would make sure you know how to do that. So know how to type it into Desmos and find that intersection. Okay. Or know how to plug it in and do algebra. And remember, we don't care about the number, we just care about the sign. Okay. So remember, from this table, not only can we identify potential maximum and minimum values, we can also see what the graph is going to look like. Okay, so if we start at the beginning interval, that's a negative slope, so it's going to be negative, undefined, negative, undefined. I should have moved that over just a tiny bit, but everywhere where we have those cusps is our undefined. And then where we have that peak would be our critical point because the derivative is 0. Okay, so then based off this table and based off of the diagram I just drew over the table, what would be our maximum value? At 0, right? Our maximum is at x equals 0. Okay, and how do we know, besides that diagram, that this is going to be a maximum? Not because it's 0. It goes from positive to negative. So notice surrounding 0, we went from a positive to a negative. So our derivatives change sign from positive to negative. That's how I know it's a maximum. So I have to mention that in my justification. So we have a maximum at x equals 0 since f prime of x changes signs from positive to negative. Okay, so that's our maximum. Where would our minimums be? The cusp, which is at x equals... Good. So the minimum is at x is equal to plus or minus 2. And then our justification is going to be the same, but we're going to write from negative to positive. Okay, any questions on 1? We shouldn't have phones out. I got evidence now. Mm.
I can't wait to play that back.
Okay. I know, I can go back. I can share it. I'm going to share it with your parents. Okay, number 2 says if h of c does not exist, then x equals c cannot be a critical point. So we're going to prove that in this example. It says find the relative max and min of the following function, which means we're going to use the first derivative test, which means we're going to take the first derivative. Okay, so we have h prime of x is equal to, and what rule would we have to use? The quotient rule. So remember, that's us taking the derivative of the top, so that's 2x times the bottom, 4 minus x, minus the function on the top, x squared, times the derivative of the function on the bottom, negative 1, all divided by 4 minus x squared. Okay, so I'm going to simplify this, make it look prettier. So I have 8x minus 2x squared plus x squared. So I just distributed the 2x and the negative x squared all over 4 minus x squared. Okay. This is equal to 8x minus x squared over 4 minus x squared. And then I can take a GCF from the numerator, and I get x times 8 minus x over 4 minus x squared. Okay, is it necessary to simplify it? No, bless you. But if we were doing the algebra by hand, would it be easier to plug it into this one or the simplified one? The simplified one. So if you're relying on decimals, then I guess it doesn't matter, right, what you type in. Okay, so then we need to figure out all our potential critical points. So when the derivative is 0 or when the derivative does not exist. So what would be the two values when the derivative is 0? Say that again. 0. X equals 0. What else? X equals 8. And what would be the potential critical point if the derivative doesn't exist? 4. So this is x equals 4. So we have 3 potential critical points. Okay. Remember, we're trying to prove that if h of c does not exist, then x equals c cannot be a critical point, which means when we make our table, we're going to notice something different, which makes one of these values not be a critical point. Okay. So we're going to create our table. So I have x and h prime of x. And then I'm going to start writing my intervals. What would be my first interval? Negative infinity to 0, which means I have 0, which I know was a critical point based off of 0 or undefined? 0. What's my next interval? 0 to 4, and then I have the potential critical point 4, which I found because the function was undefined. And then my next interval, 4 to 8, which leaves me at my critical point 8, which I found because the derivative was 0, and I'm running out of space. Well, what should I do? What should I do? I'm going to move this. Okay. And then erase that. Okay, so that can, what's nice about a tablet, right, versus your paper. And then our last interval is 8 to infinity. Okay. So then you're going to do the same thing. You're going to either use Desmos or mental math, plug in a number within that interval, and then write down the signs. So I'll give you guys a minute to do that. Or split it up among your group. Say, I'll do this interval, you do that interval. Bless you. Okay, anyone want to share? What's the first one? Yes. Negative. The next one. Positive. The next one. Positive. You should be thinking, uh-oh. Okay. Last one. Negative. So the reason why you should be thinking, uh-oh, that doesn't look right, is because do we have a sign change here? No. So that means it goes from positive and stays positive. So can that be a critical point? No, it cannot be a critical point. So I'm going to cross off x equals 4. And I'm going to say not a critical point since the sign stayed positive. I'm just going to say since positive, right? I don't got a lot of space, which means I know you guys don't have a lot of space. So no critical point since it's positive. And again, I mean because this is positive surrounding it. Okay, which means we're left with x equals 0 and x equals 8. So based off of those critical points, which one's a maximum and which one's a minimum? 8 is a max and 0 is a minimum. So we would write our justification. So we'd say we have a minimum at x equals 0 since f prime of x changes signs from which one to which one? Negative to positive, and then a maximum at x equals 8 since the derivative changes signs from positive to negative. Okay. There's one last thing on here, and that's that bold statement that we kind of skipped over because we had no space. And that statement says, what is the maximum value is not the same as saying where is the maximum value. So if you see the question, what is the maximum value, then you are answering with the y value. Okay. If it says, where is the maximum value, you're going to answer with the x value. Which makes sense, because this takes you back to algebra, right? Well, maybe algebra 2. No, I think algebra. You learned about quadratics, right? Yeah, so when you talked about quadratics and you were finding maximum, minimum, and you had those equations that said, if you throw a ball off a cliff, right? Remember those application problems? And there was a difference between when was the maximum and how long did it take to get to the maximum? Don't worry, we'll do some of those problems.